You are sitting on a rock, hurtling through space at 67,000 miles per hour, orbiting a nuclear furnace that could fit 1 million copies of your planet inside it. And yet, there is something in the universe so vast, so incomprehensibly massive, that it makes our entire solar system look like a grain of sand floating next to a continent. You have never truly understood how small you are. You think you have. You have seen the pictures. You have heard the numbers. You have watched the documentaries and nodded along as astronomers describe distances in light years and masses in solar units. But your brain cannot process it. It refuses to. Because if you truly understood the scale of what lurks at the hearts of galaxies, you would struggle to sleep tonight. This is not metaphor. This is not poetry. This is geometry and gravity, and what they do when compressed into something that should not exist. How big can a black hole actually get? The answer is worse than you think. The answer will change the way you see the night sky forever. Let us start with something familiar, something safe, something that will feel like solid ground before we pull it out from under you. Our sun is a star, a fairly ordinary one by cosmic standards. It has a diameter of roughly 864,000 miles. Light, the fastest thing in the universe, takes about 4.6 seconds to travel around its circumference. The sun contains 99.86% of all the mass in our solar system. Every planet, every moon, every asteroid, every grain of dust that has ever existed in the space between Mercury and the outer reaches of the Kuiper Belt is a rounding error compared to the sun. You could fit approximately 1.3 million Earths inside of it if you ground them up and poured them in like marbles into a jar. This is big. This is incomprehensibly big by human standards. There is nothing in your daily experience that prepares you for this scale. The largest thing you will likely ever see with your naked eyes is a mountain range. The sun is 7.7 million times larger than Mount Everest. It would take you, walking at a steady pace without rest, approximately 3,000 years to walk around its equator. And yet, the sun is nothing special. There are stars out there that make our sun look the way the sun makes Earth look. Betelgeuse, the red supergiant marking the shoulder of Orion, has a diameter roughly 700 times that of our sun. If you place Betelgeuse where the sun sits now, its surface would extend past the orbit of Mars, perhaps even Jupiter. Our planet would be consumed, vaporized, reduced to its component atoms somewhere deep inside a stellar furnace so vast that light itself would need hours to cross from one side to the other. There are stars even larger than Betelgeuse. Stephenson, 2-18, is perhaps the largest known star, with a radius over 2,100 times that of our sun. If light takes 4.6 seconds to circle our sun, it would take nearly 3 hours to make that same journey around Stephenson 2-18. This is where most conversations about cosmic scale stop. You feel appropriately humbled. You understand intellectually that you are small and the universe is large. You go about your day, but we have not yet begun. Because stars, as massive as they are fundamentally made of gas. They are diffuse. They are spread out over unimaginable volumes. A black hole is something different. A black hole takes all that mass, all that incomprehensible bulk, and crushes it into a point so small that the laws of physics as we understand them simply break down. It is not a destination. It is the end of destinations. It is where matter goes when reality itself gives up trying to describe it. And here is where our story actually begins. Because there is a type of black hole that does not form from dying stars. There is something that sits at the heart of nearly every large galaxy in the observable universe. Something that has been feeding for billions of years. Something that scientists have only recently begun to comprehend the true scale of. They are called supermassive black holes. And the word supermassive does not even begin to capture what they really are. In 1916, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I. Despite being in a war zone, he found time to do what theoretical physicists do. He solved equations. Specifically, he solved Einstein's field equations of general relativity for the gravitational field outside a spherical mass. What he found was strange. His solution predicted something called the Schwarzschild radius. This is the critical size to which any mass must be compressed before gravity becomes so overwhelming that nothing, not matter, not radiation, not even light itself, can escape. Schwarzschild showed that this radius is directly proportional to the mass of the object. The formula is elegant in its simplicity. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For our Sun, this radius is about 1.86 miles. If you could somehow compress all the mass of our Sun, all 1.99 octillion kilograms of it, into a sphere less than 4 miles across, you would create a black hole. Earth's Schwarzschild radius is even smaller, about 9 millimeters, roughly the size of a peanut. Your entire planet compressed to the size of a peanut. Everything you have ever known, everything humanity has ever built, every ocean and mountain and forest squeezed into something you could hold between 2 fingers. For decades, black holes remained theoretical curiosities, mathematical artifacts that emerge from Einstein's equations, but which surely could not exist in reality. Physicists argued about whether nature could actually produce such extreme objects. Then astronomers started looking at the centers of galaxies, and everything changed. In the 1990s, a team led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics began tracking individual stars near the center of our own Milky Way galaxy. They focused on a region called Sagittarius A star, a powerful source of radio waves located roughly 26,000 light-years from Earth. What they found was impossible to explain with ordinary physics. There were stars orbiting something invisible, stars traveling at speeds that made no sense. One star in particular, designated S2, was completing an orbit around an invisible point every 16 years. At its closest approach, S2 swings within just 11 billion miles of this unseen object, traveling at 17 million miles per hour, about 3% of the speed of light. That is fast enough to cross the entire diameter of Earth in less than 3 seconds. The orbital mechanics were clear. For S2 to travel that fast without flying off into deep space, it had to be orbiting something with a mass of approximately 4.3 million suns. But there was nothing visible there. No star, no cluster of stars, nothing but radio waves and X-rays emanating from a region smaller than our solar system. There was only one explanation consistent with the data: a black hole. Not a stellar mass black hole formed from a dying star. Something far larger, something far stranger, something millions of times more massive than our Sun, compressed into a region from which not even light can escape. Genzel and his collaborator, Andrea Ghez, would eventually share the 2020 Nobel Prize in Physics for this discovery, recognition of their patient decades-long work, proving that the impossible was real. In 2022, the Event Horizon Telescope collaboration released an image that confirmed what the orbital data had suggested. They had photographed Sagittarius A star directly, revealing a glowing ring of superheated matter surrounding a dark void. The shadow of a supermassive black hole, the shadow of the monster that has been lurking at the heart of our home galaxy for billions of years, patient and silent and utterly indifferent to our existence. But here is the thing about Sagittarius A star. By supermassive black hole standards, it is small. The black hole at the center of the Milky Way has an event horizon, the boundary beyond which nothing can escape, with a diameter approximately half the size of Mercury's orbit around the Sun. This means that if you placed Sagittarius A star where our Sun sits, its edge would extend outward about 15 million miles. Mercury, at its closest approach to the Sun, comes within 29 million miles. So our central black hole would still fit comfortably inside Mercury's orbital path. 4 million solar masses, compressed into a sphere smaller than Mercury's orbit. This seems impossibly large until you realize that Sagittarius A star is, by the standards of supermassive black holes, actually quite modest. It is a lightweight among cosmic heavyweights, a minor player in a universe of gravitational titans. And that realization should terrify you. The Andromeda Galaxy, our closest large galactic neighbor at 2.5 million light-years away, harbors a black hole with a mass of roughly 140 million suns. That is 35 times more massive than our own galactic center. Its event horizon would be correspondingly larger, perhaps consuming the entire inner solar system if placed at the location of our Sun. But even this begins to pale in comparison to what astronomers have discovered in more distant galaxies. In the constellation Virgo, about 55 million light-years from Earth, sits the giant elliptical galaxy Messier 87. This was the galaxy that produced the first direct image of a black hole, released by the Event Horizon Telescope in April 2019. The image showed the same basic structure as Sagittarius A star, a ring of incandescent matter surrounding a dark void, but the scale was utterly different. The black hole at the center of M87, designated M87 star, has a mass of 6.5 billion suns. Not million, billion. That is 1,500 times more massive than our own galactic black hole. According to NASA, its shadow is so large that a beam of light traveling at 670 million miles per hour would take approximately 2.5 days just to cross from one side to the other. Think about what that means. Light is the cosmic speed limit. Nothing can travel faster, and light would need more than 60 hours to traverse the dark zone around M87's black hole. If you placed M87 star at the center of our solar system, its event horizon would extend past the orbit of Neptune. It would swallow every planet, every asteroid, every fragment of ice and rock in the Kuiper belt. The edge of this black hole would sit somewhere around 12 billion miles from where the Sun used to be, in the cold outer reaches of what was once our cosmic neighborhood. But M87 star is not the largest black hole we have found. Not even close. Let that comparison settle in for a moment. Neptune's orbit, the boundary of what most people consider the solar system proper, takes light about 4 hours to cross. That entire region, everything from the scorching surface of Mercury to the frozen methane storms of Neptune, would disappear inside the event horizon of M87's black hole. Earth's orbit around the Sun, the familiar 93 million mile journey we complete every year, would occur deep inside this gravitational prison. The sheer absurdity of this scale becomes clearer when you think about human history within the context of light-speed communication. If you could somehow stand on the event horizon of M87's black hole and shout to a friend standing on the opposite side, your message would take over 2 days to reach them, even though you are both standing on the same gravitational boundary. In that same 2-day span, light from our sun could travel to Jupiter and back several times. The distances involved are not astronomical in the casual sense. They are astronomical in the terrifying, reality-bending sense. And still, there are larger black holes waiting to be described. In the constellation Canis Venatici, near the border with Coma Berenices, there is a quasar called TON 618. A quasar is the luminous core of a distant galaxy, powered by matter falling into a supermassive black hole. The accretion disk, the swirling vortex of gas and dust spiraling toward the event horizon, heats up to temperatures exceeding 10 million degrees as it falls. This superheated material emits radiation across the entire electromagnetic spectrum, making quasars among the brightest objects in the known universe. TON 618 shines with the light of 140 trillion suns. That is a number so large it has no intuitive meaning. Our entire Milky Way galaxy, with its 100 to 400 billion stars, is roughly 1,000 times less luminous than this single quasar. The light we see from TON 618 today left that distant corner of the universe approximately 10.8 billion years ago, when the cosmos was less than 3 billion years old. We are seeing this object as it existed when the universe was still in its adolescence. And at the heart of TON 618 sits a black hole with a mass that scientists initially struggled to believe. The measurements come from a technique called reverberation mapping. Astronomers study the emission lines in the quasar's spectrum, which are produced by gas clouds orbiting far from the black hole's event horizon. The brightness of the quasar illuminates these clouds, and by measuring the time delay between variations in the quasar's brightness and corresponding variations in the emission lines, scientists can determine how far away the gas clouds are. Combined with measurements of how fast the gas is moving, this allows a calculation of the central mass. For TON 618, the results were staggering. The emission lines in its spectrum are unusually broad, indicating that surrounding gas is traveling at extraordinary speeds, with some measurements suggesting velocities around 10,500 kilometers per second. This implies a black hole with a mass between 40 and 66 billion times that of our Sun. Let us take the higher estimate. A black hole with 66 billion solar masses would have a Schwarzschild radius of approximately 1/300 astronomical units. An astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. This means the event horizon of TON 618 extends outward about 121 billion miles from its center. To put this in perspective, the distance from the Sun to Pluto is about 39 astronomical units. The event horizon of TON 618 is more than 40 times farther from its center than Pluto is from the Sun. If you place this black hole where our Sun currently sits, its edge would extend far beyond the orbit of every known object in our solar system. The entire structure of planets, moons, dwarf planets, and Kuiper Belt objects that we call home would be absorbed, consumed, erased. According to NASA, a beam of light traveling at its constant speed of 670 million miles per hour would need weeks to traverse the shadow of TON 618. Not hours, weeks. And yet, even this monster is not the largest we have found. Consider for a moment what weeks to traverse actually means. When NASA says light would need weeks to cross the shadow of Ton 618, they are describing a region of absolute darkness larger than any single object you have ever encountered or will ever encounter. This black sphere of nothingness from which no light escapes, no information returns, no probe could ever report back, is so vast that you could fit multiple solar systems inside it with room to spare. If you could somehow travel at the speed of light, the cosmic speed limit itself, it would take you approximately 15 days just to fly from one edge of Ton 618's event horizon to the other. In that same time, light from the Sun reaches past the orbits of Uranus and Neptune, almost to the edge of the heliosphere. Ton 618's shadow is a void the size of a small constellation, invisible because it is too dark, detectable only by its gravitational influence on everything around it. The gas falling into Ton 618 moves at over 10,000 kilometers per second. That is 22 million miles per hour. At that speed, you could travel from Earth to the Moon in under 40 seconds. And yet, even at those unimaginable velocities, matter takes significant time to spiral inward, losing energy to radiation, heating up to millions of degrees, illuminating the universe with the light of 140 trillion suns before finally disappearing behind the event horizon. Ton 618 is so massive that it exceeds the total stellar mass of our entire galaxy. The Milky Way contains an estimated 64 billion solar masses worth of stars. Ton 618's black hole alone is 66 billion solar masses. This single point of absolute darkness outweighs every star, planet, asteroid, and dust grain in the galaxy you call home. But even this is not the end of the scale. In the southern constellation of Phoenix, about 5.8 billion light-years from Earth, there is a galaxy cluster designated SPTCL J23444243, more commonly known as the Phoenix Cluster. Galaxy clusters are the largest gravitationally bound structures in the universe, collections of hundreds or thousands of galaxies held together by their mutual gravity and vast quantities of dark matter. The Phoenix Cluster is one of the most massive such structures ever discovered. At the center of this cluster sits a galaxy called Phoenix A, a giant elliptical galaxy that produces more X-rays than any other known cluster center. This galaxy is in the grip of a runaway cooling flow, meaning that hot intergalactic gas is condensing onto it at an extraordinary rate. Stars are forming within Phoenix A at a pace of roughly 740 new suns per year. For comparison, the Milky Way produces approximately 1 new star per year. All of this cosmic activity is driven by something lurking at the center of Phoenix A, based on theoretical models of how supermassive black holes grow and interact with their host galaxies. Scientists have estimated that the central black hole of Phoenix A has a mass on the order of 100 billion solar masses, 100 billion suns. This is not a definitive measurement. Unlike Sagittarius A star, where we can track individual stars orbiting the black hole, or Ton 618, where we can analyze the spectrum of its quasar emission, Phoenix A's black hole mass is estimated through indirect methods involving the galaxy's stellar dynamics and the energetics of its active nucleus. But if the models are correct, this is the most massive black hole known in the observable universe. A black hole of 100 billion solar masses would have a Schwarzschild radius of approximately 2,000 astronomical units, or about 0.03 light-years. Its event horizon would be roughly 590 billion kilometers across, some 366 billion miles in diameter. This is 100 times the distance from the Sun to Pluto. If you were to place Phoenix A's black hole at the center of our solar system, not only would every planet be consumed, but the event horizon would extend so far outward that it would approach the inner edge of the Oort cloud, the distant shell of icy objects that marks the outermost boundary of the Sun's gravitational influence. The circumference of this black hole's event horizon is so vast that light itself, traveling at its universal speed limit, would require approximately 71 days to complete a single lap around it. Nearly 2.5 months of continuous travel at 670 million miles per hour just to circle the edge of nothing. To help ground this in something approaching human experience, consider this. If you boarded a spacecraft traveling at the speed of light on January the 1st and set out to orbit Phoenix A's event horizon, you would not complete the journey until mid-March. Christmas would have come and gone. New Year's celebrations would be a distant memory, and you would still be tracing the outline of a single black hole. Now consider that a commercial airliner traveling at 550 miles per hour would need approximately 100 million years to complete that same circumference. Every flight you have ever taken, every journey across oceans and continents is rendered meaningless against this scale. The entire history of commercial aviation, every mile ever flown by every aircraft since the Wright brothers, does not approach a single orbit of this object. The mass of Phoenix A's black hole is estimated at 100 billion suns. To put that number in perspective, if you counted one number per second, it would take you over 3,000 years to count to 100 billion. And that is just counting to the number. The actual mass involved is 100 billion objects, each one a nuclear furnace capable of sustaining planetary systems for billions of years, all compressed into a region of space-time so curved that light itself cannot escape. This is what supermassive actually means. This is the true scale of the objects that sit at the hearts of galaxies. Objects so large that they defy our ability to conceptualize them. Objects so dense that they warp the fabric of space-time so severely that time itself begins to lose meaning. Objects that have been there since the universe was young, feeding and growing, silent and patient, waiting for matter to wander close enough to consume. And this is where things get truly disturbing. What would happen if you were to approach one of these cosmic titans? For a stellar mass black hole, the kind formed when a massive star collapses, the answer is violent and immediate. As you approach, the difference in gravitational pull between your feet and your head becomes catastrophic. Stephen Hawking described this phenomenon in A Brief History of Time, coining a term that has since entered the scientific lexicon: spaghettification. The tidal forces near a stellar mass black hole are so extreme that you would be stretched vertically and compressed horizontally, drawn out into a long, thin strand of matter, like a piece of cosmic pasta. This would happen well before you reached the event horizon, perhaps thousands of kilometers from the point of no return. The forces would tear apart every molecular bond in your body, reducing you to a stream of individual atoms falling into the void. But supermassive black holes are different. There is a simple equation that describes the tidal acceleration a body experiences near a massive object. The key relationship is that this tidal force is proportional to the mass of the black hole, but inversely proportional to the cube of the distance from it. Because the Schwarzschild radius increases linearly with mass, while the tidal forces decrease with the cube of distance. Larger black holes actually have gentler conditions at their event horizons than smaller ones. For a stellar mass black hole of 1 solar mass, an astronaut falling feet first would experience tidal accelerations on the order of 19 billion meters per second squared at the event horizon. This is roughly 2 billion times the acceleration due to gravity at Earth's surface. Your body would be torn apart long before reaching that point. But for a supermassive black hole like Sagittarius A star with 4.3 million solar masses, the tidal acceleration at the event horizon is far more gentle. For a black hole with 100 million solar masses or more, the tidal forces at the event horizon become so weak that they are actually less than what you feel standing on Earth's surface right now. This means something remarkable and terrifying. You could cross the event horizon of a supermassive black hole without feeling anything at all. There would be no special sensation, no cosmic alarm bell, no physical indicator that you had passed the point of no return. Your body would remain intact, your heart would continue to beat, your neurons would continue to fire. You would be alive, conscious, and utterly doomed, with no way to communicate that fact to anyone outside. Think about what this means. You are falling toward absolute darkness, toward a region from which nothing escapes, toward the end of all possible futures that lead back to the universe you knew. And you feel nothing unusual. The sky above you has shifted into strange configurations, light bending around the gravitational monster you are approaching. But you yourself experience nothing more dramatic than a pleasant float in microgravity. The event horizon is not a physical barrier. It is a mathematical surface, a boundary in space-time defined by geometry rather than matter. On one side, escape is possible if you have enough velocity. On the other side, all paths through space-time, no matter how you orient them, no matter how fast you try to go, lead inexorably toward the center. Inside the event horizon, the singularity is not a place in space. It is a moment in your future, as inevitable as tomorrow. This is difficult to comprehend because our intuitions about space and time break down in these extreme environments. Inside the event horizon, the direction toward the singularity is no longer down in any meaningful sense. It is later. You cannot avoid the singularity for the same reason you cannot avoid next Tuesday. Time itself has been so warped by the black hole's gravity that what was once a direction in space has become a direction in time. And from the perspective of someone watching you fall, something equally strange would happen. Gravity bends space-time. This is the core insight of Einstein's general relativity, the theoretical framework that predicts black holes in the first place. Near a massive object, time passes more slowly relative to a distant observer. This effect, called gravitational time dilation, has been measured with atomic clocks on Earth. Clocks at higher altitudes, farther from Earth's mass, tick slightly faster than clocks at sea level. GPS satellites must account for this discrepancy, or their positioning calculations would drift by kilometers per day. Near a black hole, this effect becomes extreme. Imagine watching a friend fall toward the event horizon of a supermassive black hole. From your vantage point, safely distant from the gravitational monster, you would see something peculiar. As your friend approaches the event horizon, they would appear to slow down. Their movements would become sluggish, as if they were moving through increasingly thick honey. the light reaching your eyes from their body would shift toward the red end of the spectrum as photons struggle to climb out of the deepening gravity well. As your friend reaches the event horizon itself, they would appear to freeze entirely, not because anything physical has happened to them, but because time itself, as measured by you, has essentially stopped at that boundary. The light that would show them crossing the horizon would be so severely redshifted that it would fade to invisibility. You would see them become dimmer and dimmer, redder and redder, more and more frozen, until they faded from view entirely, like a photograph exposed to the sun. From your perspective, your friend never actually crosses the event horizon. They approach it asymptotically, their image smeared across the boundary for all eternity. But from your friend's perspective, nothing special happens at all. They fall past the event horizon, their personal clock ticking normally. They might have seconds or minutes, or, in the case of the largest supermassive black holes, hours or even days of subjective experience remaining before tidal forces finally begin to stretch them apart as they approach the singularity. This is not science fiction. This is what the mathematics of general relativity predicts, and every experimental test we have ever devised has confirmed general relativity's predictions to extraordinary precision. The S2 star orbiting Sagittarius A star follows precisely the path that Einstein's equations predict, including a subtle precession of its orbit, a rosette pattern caused by the warping of spacetime around the black hole. In 2020, the Gravity collaboration confirmed this Schwarzschild precession through nearly 3 decades of observations. The equations work. Black holes behave exactly as Einstein predicted over a century ago, which means these implications about time and inescapability are almost certainly correct. There is another phenomenon that becomes profoundly important at these scales: the accretion disk. Black holes themselves emit nothing except, theoretically, an infinitesimal amount of Hawking radiation, far too faint to detect. But the material falling toward a black hole does not remain silent. Matter spiraling toward the event horizon forms a rotating disk, and within this disk, particles collide, exchange energy, and experience friction. This friction converts gravitational potential energy into heat, and that heat becomes radiation. The physics of accretion disks is remarkably efficient. When matter falls onto a black hole via an accretion disk, approximately 10% of its rest mass can be converted into energy. For comparison, nuclear fusion in the core of a star converts less than 1% of matter into energy. Accretion onto black holes is roughly 30 times more efficient than the nuclear reactions that power stars. This is why quasars are so bright. TON 618, with its 140 trillion solar luminosities, is powered by matter falling into its central black hole at an extraordinary rate. The accretion disk reaches temperatures of millions of degrees, emitting radiation across the electromagnetic spectrum, from radio waves to X-rays. In the innermost regions of the disk, matter orbits at velocities approaching significant fractions of the speed of light, heated by compression and friction to temperatures that would vaporize any known substance. The innermost stable circular orbit around a black hole, the closest you can orbit without inevitably spiraling in, is located at 3 times the Schwarzschild radius for a non-rotating black hole. Inside this boundary, there are no stable orbits. Any matter that crosses this threshold is doomed to fall into the event horizon. For Phoenix A's hypothetical 100 billion solar mass black hole, this innermost stable orbit would be located about 6,000 astronomical units from the singularity. That is roughly 150 times the distance from the Sun to Pluto. And matter would be orbiting there at velocities that defy everyday intuition, radiating energy at rates that would outshine entire galaxies. The supermassive black hole at the center of M87 produces relativistic jets, streams of particles accelerated to nearly the speed of light and shot outward perpendicular to the accretion disk. These jets extend thousands of light years into intergalactic space. The jet emanating from M87 is tens of millions of times larger than the black hole's event horizon, a geyser of energy driven by processes we still do not fully understand. In 2024, the Event Horizon Telescope collaboration and other observatories detected a tera-electron-volt gamma-ray flare from M87's black hole, the first such flare observed in over a decade. This burst of ultra-high energy radiation emerged from a region just a few light days across, smaller than our solar system, yet carrying enough energy to dwarf the output of an entire stellar population. These are not static objects. They are engines, cosmic furnaces powered by gravity itself, converting matter into energy at rates that we struggle to comprehend. So where does this leave us? What are we supposed to do with the knowledge that objects this massive, this dangerous, this fundamentally alien to human experience actually exist? Scientists have proposed a theoretical upper limit to how massive a black hole can grow. There are feedback mechanisms involved. As a black hole accretes matter, radiation pressure from the accretion disk can push material away, starving the black hole of fuel. The Eddington limit describes the maximum luminosity a body can achieve when gravity and radiation pressure are in balance. Beyond this point, radiation drives matter outward rather than allowing it to fall inward. Calculations suggest this limit places a ceiling on black hole masses at around 50 to 100 billion solar masses. Phoenix A, if the mass estimates are correct, sits right at this theoretical boundary. It may be not just the largest black hole we have found, but close to the largest black hole that can possibly exist under the physics we currently understand. But the universe has surprised us before. Some theorists have proposed the existence of stupendously large black holes, objects with masses exceeding 100 billion suns, potentially reaching into the trillions. These hypothetical monsters might have formed through different mechanisms in the early universe, perhaps seeded by primordial fluctuations in the Big Bang itself, rather than grown through ordinary accretion. We do not know if they exist, but we also did not know supermassive black holes existed until we went looking for them. What we do know is this: nearly every large galaxy in the observable universe contains a supermassive black hole at its center. The Milky Way has one. Andromeda has one. M87 has one. Phoenix A has one. There are hundreds of billions of galaxies within the observable universe. Each one likely harbors a gravitational monster at its core. You are surrounded by these things, in a cosmic sense. Every direction you look, if you peer far enough into space, you are looking toward a supermassive black hole. They are woven into the fabric of how galaxies form and evolve. The mass of a galaxy's central black hole correlates with the mass of the galaxy's central bulge, suggesting a deep connection between black hole growth and galactic evolution that we are only beginning to understand. And our own supermassive black hole, modest though it may be by cosmic standards, has shaped the Milky Way we inhabit. Stars in our galactic center orbit it at tremendous speeds. It has likely consumed countless stars, planets, and gas clouds over the 13 billion-year history of our galaxy. It sits there now, relatively quiet, 26,000 light-years away, a dormant giant waiting for its next meal. In approximately 4 billion years, the Andromeda Galaxy and the Milky Way will collide. This is not speculation. It is inevitable, written in the gravitational equations that govern the motion of galaxies. The two supermassive black holes at their respective centers, Sagittarius A star and Andromeda's 140 million solar mass behemoth, will eventually find each other across the chaos of the merger. When supermassive black holes merge, they produce gravitational waves, ripples in space-time itself, predicted by Einstein and first detected by LIGO in 2015. But the gravitational waves from stellar mass black holes are at frequencies we can detect with ground-based instruments. Supermassive black hole mergers produce gravitational waves at much lower frequencies, requiring detectors millions of kilometers in scale. NASA and the European Space Agency are collaborating on a mission called LISA, the Laser Interferometer Space Antenna, which will deploy 3 spacecraft in orbit around the Sun, shooting lasers at each other across millions of kilometers to detect these low-frequency ripples. When LISA launches, perhaps in the next decade, we will have a new window onto the universe of supermassive black holes. We will be able to hear them merging across cosmic time, listening to the universe's largest objects collide and combine. The ultimate fate of our merged galaxy's central black hole is unknown. It will grow larger with each merger, each accretion event, each star that wanders too close. Billions of years from now, the universe will be very different. Expansion will have carried most galaxies beyond our cosmic horizon. Stars will have burned out. Even the supermassive black holes will eventually evaporate, hawking radiation, slowly draining away their mass over timescales that make the current age of the universe look like the blink of an eye. But that is unimaginably far in the future. Right now, in this moment, the universe is filled with these extraordinary objects. They sit at the centers of galaxies, warping space-time around them, swallowing light, distorting time itself. They are so large that their dimensions require new intuitions to grasp. They are so dense that they represent the ultimate endpoint of gravitational collapse. And they are so powerful that they can outshine trillions of stars while remaining, at their hearts, perfectly and absolutely dark. Let us return to where we started. You are sitting on a rock, hurtling through space, orbiting a star that could fit 1 million Earths inside it. That star is one of perhaps 400 billion in a galaxy held together by 4.3 million solar masses of absolute darkness at its center. That darkness has an event horizon half the size of Mercury's orbit, and it is one of the smallest supermassive black holes we know of. Elsewhere in the universe, black holes weigh billions of times more than our Sun. Their event horizons span distances that dwarf our entire solar system. Light takes weeks to cross their shadows. Time slows to a crawl at their edges and stops entirely at their hearts. They consume matter with an efficiency that makes stars look wasteful, and they have been growing, feeding, merging for billions of years. Phoenix A may contain a 100 billion suns worth of mass, compressed into a sphere that light would need 71 days to circumnavigate. It is so large that the entire architecture of planets we call home, from Mercury to the distant objects of the Kuiper Belt, would vanish inside its horizon with room to spare. It is so massive that it challenges our theoretical understanding of how black holes can grow. And it is only one of countless supermassive black holes scattered throughout the cosmos. You live in a universe of monsters, not metaphorical ones, real ones, objects that Einstein's equations predicted over a century ago and that we have only recently confirmed are exactly as strange, as vast, as fundamentally incomprehensible as the mathematics suggested. The next time you look up at the night sky, remember that behind every galaxy you can see, and every one you cannot, there is something waiting at the center, something patient, something that has all the time in the universe because time itself bends to its will, something so massive that it took 10,000 words just to gesture at its scale. And even then, we have only scratched the surface of what these objects truly are. You are small, the universe is large, and at the hearts of galaxies, gravity has built temples to its own power, structures so extreme that they mark the boundary between what we can understand and what we can only describe. This is not terrifying. This is awe. This is the universe showing you exactly what it is capable of, what it has been doing long before you existed, and what it will continue doing long after you are gone, forever and ever, until time itself ends. The scale is inhuman because the universe was not built for humans. We are guests here, permitted to witness wonders that care nothing for our existence. And that somehow makes it even more beautiful. But we are not finished yet, because there is one more aspect of supermassive black holes that we have not fully explored. One more dimension to their existence that reveals just how deeply these objects are intertwined with our cosmic history. You see, supermassive black holes are not just passive consumers of matter. They are sculptors of galaxies. They are architects of the cosmic web. Without them, the universe you inhabit might not exist in any recognizable form. The relationship between a supermassive black hole and its host galaxy is one of the most fascinating discoveries in modern astrophysics. There is a correlation discovered in the late 1990s and early 2000s called the M-sigma relation. The mass of a central black hole correlates tightly with the velocity dispersion of stars in the galactic bulge. Galaxies with faster-moving central stars harbor more massive black holes. The correlation is remarkably precise, far more precise than you would expect if the black hole and the galaxy grew independently. This suggests something profound. The black hole and the galaxy must be connected. They must grow together, influence each other, evolve in tandem. But how? The black hole is tiny compared to the galaxy. The event horizon of Sagittarius A star would fit inside our solar system, while the Milky Way stretches across 100,000 light years. How can something so relatively small shape something so incomprehensibly large? The answer is energy. When a supermassive black hole actively accretes matter, the energy released is staggering. We talked about quasars earlier, objects like TON 618 that outshine entire galaxies. This radiation does not simply escape into the void. It interacts with the gas surrounding the black hole, heating it, pushing it, sometimes driving it out of the galaxy entirely. This process is called AGN feedback, where AGN stands for active galactic nucleus. The black hole's feeding frenzy releases so much energy that it can suppress star formation throughout the host galaxy. The hot gas that would otherwise cool and collapse to form new stars is kept diffuse and unproductive. The black hole regulates its own food supply and, in doing so, regulates the entire galaxy's evolution. There is a cosmic thermostat at work here. When the black hole feeds too vigorously, its energy output heats the surrounding gas and cuts off the supply. When the gas cools again, accretion resumes. This back and forth, playing out over billions of years, synchronizes the growth of the black hole with the growth of its galactic host. Without this feedback mechanism, galaxies might look very different. Simulations suggest that without AGN feedback, galaxies would form far more stars than we actually observe. The universe would be brighter, but also fundamentally altered in ways we can barely imagine. The supermassive black holes are not just passengers in galactic evolution. They are drivers. And here is where things become personal. Our own galaxy, the Milky Way, exists in a particular state because of the supermassive black hole at its center. Sagittarius A star is currently dormant, accreting matter at an extremely low rate. But it was not always so quiet. Evidence suggests that Sagittarius A star experienced periods of much more vigorous activity in the past. In 2010, astronomers announced the discovery of two enormous structures extending above and below the galactic plane, lobes of high-energy radiation that stretch 25,000 light-years in each direction. These Fermi bubbles, named after the Fermi Gamma Ray Space Telescope that detected them, are likely the remnants of a massive outburst from our central black hole millions of years ago. Something fed Sagittarius A star a large meal, perhaps a gas cloud, perhaps an unfortunate star, and the resulting energy release inflated these bubbles like cosmic balloons, pushing hot gas out of the galactic center at speeds exceeding 2 million miles per hour. This happened while our ancestors were walking the Earth. Anatomically, modern humans have existed for roughly 300,000 years. The Fermi bubbles are estimated to be between 1 and 3 million years old. Early hominids might have looked up at the night sky, while 26,000 light-years away, the heart of the galaxy was erupting with enough energy to reshape its surroundings. They would not have seen it directly. The light from such an event would have been obscured by the dense star fields and dust clouds between us and the galactic center. But the remnants of that explosion are still there, still glowing in gamma rays, still expanding outward, a record of cosmic violence written in the structure of our home galaxy. There is also the question of origins. Where did supermassive black holes come from? This remains one of the great unsolved problems in astrophysics. We know that stellar mass black holes form when massive stars collapse at the end of their lives. A star with more than about 25 times the mass of our Sun will end its life in a supernova, leaving behind a black hole with a mass of perhaps 5 to 100 solar masses. But how do you get from there to millions or billions of solar masses? The universe is only 13.8 billion years old, and yet we observe quasars powered by billion solar mass black holes at redshifts corresponding to when the universe was less than 1 billion years old. How can black holes grow so massive, so quickly? There are three main theories. The first is that supermassive black holes grew from smaller seeds through continuous accretion and mergers over cosmic time. Start with stellar mass black holes in the early universe. Let them feed on surrounding gas. Let them merge when galaxies collide. And given enough time, you might build up something truly massive. The problem is that there may not have been enough time. Accretion has limits. The Eddington limit caps how fast a black hole can grow by balancing gravitational attraction against radiation pressure. Even feeding at the maximum Eddington rate, it would take a stellar mass black hole longer than the age of the universe to reach 1 billion solar masses. The second theory involves direct collapse black holes. In the very early universe, before the first stars formed, there may have been pockets of gas that collapsed directly into black holes without ever forming a star at all. These seed black holes could have started with masses of thousands or even hundreds of thousands of suns, giving them a head start in the growth race. The third theory proposes primordial black holes, objects that formed not from collapsing matter, but from density fluctuations in the earliest moments after the Big Bang. If regions of the infant universe were dense enough, they could have collapsed into black holes before matter, as we know it, even existed. These primordial black holes, if they exist, could have seeded the supermassive monsters we see today. We do not know which of these scenarios is correct. Perhaps all of them contribute in different circumstances. The James Webb Space Telescope has already begun discovering unexpectedly massive black holes in the very early universe, objects that challenge our understanding of how quickly these cosmic giants can form. The mystery deepens even as our observations improve. There is one more phenomenon we should explore before we conclude. It is perhaps the most dramatic display of a supermassive black hole's power: tidal disruption events. When a star wanders too close to a supermassive black hole, it can be destroyed by tidal forces, not swallowed whole, but shredded. The gravitational gradient across the star's diameter becomes so steep that the near side is pulled more strongly than the far side, and the star is stretched apart into a stream of stellar debris. Half of this material is flung outward on escape trajectories, lost to the cosmos forever. The other half remains bound to the black hole, falling back toward the event horizon in a cascade of gas that forms a temporary accretion disk. This disk heats up rapidly, producing a distinctive flare of radiation that astronomers can detect across billions of light years. These tidal disruption events are cosmic homicides, snapshots of stars being murdered by gravity. They provide unique laboratories for studying black holes because we can watch the entire process unfold in real time. The flare rises over weeks as debris returns to the black hole, then fades over months to years as the material is gradually consumed. In 2022, astronomers observed one of the most distant tidal disruption events ever detected, occurring when the universe was less than 1/3 its current age. A supermassive black hole, estimated at 100 million to 1 billion solar masses, destroyed a star and produced a flare visible across 8.5 billion light years. These events are not rare on cosmic timescales. Astronomers estimate that a typical galaxy experiences a tidal disruption event once every 10,000 to 100,000 years. In a universe containing hundreds of billions of galaxies, that means thousands of stars are being shredded by supermassive black holes somewhere in the cosmos every single day. As you read this sentence, somewhere in the observable universe, a star is being stretched into nothingness, its matter streaming toward an event horizon it will never cross from our perspective, feeding a darkness that has been waiting for billions of years. We have talked about size. We have talked about mass. We have talked about time dilation and accretion disks and tidal forces, but perhaps the most profound aspect of supermassive black holes is what they represent philosophically. These cosmic objects are the ultimate expression of gravity's power. Einstein showed us that gravity is not a force in the traditional sense, but a curvature of space-time caused by the presence of mass and energy. Near a supermassive black hole, this curvature becomes so extreme that it fundamentally alters the nature of space and time. Time slows, distances warp, light bends. Causality itself, the fundamental principle that causes must precede effects, becomes constrained in ways that make no intuitive sense. Inside the event horizon, the singularity is not a place you can choose to avoid. It is a moment in your future, as inevitable as death, as certain as mathematics. And at the singularity itself, if such a thing truly exists, the curvature of space-time becomes infinite. Our equations break down. General relativity, the most successful theory of gravity ever devised, fails to describe what happens at that point. This is called a singularity precisely because it is singular, a place where our understanding of the universe reaches its limits. We know that general relativity cannot be the complete story. Quantum mechanics, the other pillar of modern physics, must somehow be combined with gravity to produce a theory of quantum gravity that can describe what happens at the center of a black hole. But despite decades of effort, that theory remains elusive. The singularity remains a mystery, a blank spot on the map of physics where we have written, "Here be dragons." Some physicists suspect that singularities do not actually exist, that quantum effects prevent the complete collapse to infinite density. Others believe that the singularity is shielded from the rest of the universe by the event horizon precisely because whatever happens, there would be too strange for our universe to tolerate being visible. This is called cosmic censorship, and it remains an unproven conjecture. The truth is, we do not know what happens at the center of a black hole. We may never know. The event horizon ensures that whatever occurs inside can never send information back to us. Black holes keep their deepest secrets hidden behind a wall of space-time curvature, forever inaccessible to outside observation. And yet, there may be one way information escapes. In 1974, Stephen Hawking made a prediction that would become one of the most famous results in theoretical physics. Using the tools of quantum field theory applied to the curved space-time around a black hole, he showed that black holes are not truly black. They emit radiation. The mechanism is subtle. In quantum mechanics, empty space is not truly empty. It seethes with virtual particle pairs, particles and antiparticles that pop into existence for the briefest moment before annihilating each other. Near the event horizon of a black hole, something strange can happen. One member of a virtual pair can fall into the black hole, while the other escapes to infinity. The escaped particle carries away energy, which must come from somewhere. It comes from the black hole itself. Over unimaginably long timescales, this Hawking radiation causes black holes to evaporate. The process is absurdly slow. A black hole with the mass of our Sun would take approximately 10⁻⁶7 years to evaporate, a number so large it makes the current age of the universe look instantaneous. For a supermassive black hole like Phoenix A, the evaporation time would be longer still, perhaps 10⁻100 years or more. These are timescales that render the word eternal almost meaningless. The universe itself will have died a heat death trillions of years before the largest black holes finally blink out of existence. But eventually, if the physics is correct, even these cosmic monsters will fade away. And when they do, what happens to the information they swallowed? This is the black hole information paradox, and it has tormented physicists for half a century. Does information about what fell into a black hole get destroyed? Does it somehow get encoded in the Hawking radiation? Does it escape through some other mechanism we have not yet discovered? We do not know. The answers may require a theory of quantum gravity we do not yet possess. But the questions themselves are extraordinary. They touch on the deepest issues in physics: the nature of information, the structure of space-time, the ultimate fate of matter and energy in a universe governed by relentless gravitational collapse. So where does this leave us? You live in a universe that contains objects so massive they bend the fabric of reality itself. Objects so large that light needs weeks or months to cross their shadows. Objects so powerful they shape the evolution of entire galaxies. Objects so strange that time slows to a stop at their edges and our physics fails to describe their centers. These are not abstract mathematical curiosities. They are real. Sagittarius A star sits 26,000 light-years away, warping the orbits of stars we can actually observe. M87's black hole has been photographed, its shadow revealed in radio waves collected by telescopes spanning the globe. Quasars like TON 618 outshine trillions of suns across billions of light-years of cosmic distance. You have spent your entire life in a universe dominated by these objects, and you never knew the true scale of what was out there. Most people do not. Most people live their lives without ever confronting the reality that the centers of galaxies are occupied by gravitational monsters that dwarf everything else in existence. But now you know. You know that our sun, as large as it seems, is cosmically insignificant. You know that our galaxy harbors a 4 million solar mass darkness at its heart. You know that other galaxies contain black holes 100 billion times more massive than our sun, with event horizons larger than our entire solar system. You know that these objects have been growing and feeding and merging for billions of years and will continue to do so for billions of years more. And you know that despite all this, despite the incomprehensible scales and the terrifying implications, the universe goes on. Stars form, planets orbit, life evolves, intelligence emerges. Beings like you ask questions about the nature of existence and find, to their astonishment, that the answers are far stranger than anything they could have imagined. The true scale of a supermassive black hole is not a number. It is not a comparison to familiar objects. It is a revelation about the nature of reality itself. It is a reminder that the universe operates on scales that human intuition was never designed to comprehend. It is an invitation to wonder, to curiosity, to the profound humility that comes from confronting the cosmic truth of your own insignificance. You are small, but you are also aware. You know these things exist. You can comprehend, even imperfectly, the mathematics that describe them. You can feel awe at their scale and terror at their power and profound beauty in their existence. That makes you remarkable. Out of all the matter in the universe, out of all the stars and planets and gas clouds and black holes, you are among the tiny fraction that knows. You are matter contemplating itself, gravity thinking about gravity, the universe becoming aware of its own extraordinary contents. The supermassive black holes do not know they exist. They cannot appreciate their own scale. But you can. And that, perhaps, is the most astonishing thing of all. Before we end, let us return one more time to the numbers, the scale, the sheer reality of what we have described. Sagittarius A star, 4.3 million solar masses. Event horizon half the size of Mercury's orbit, located 26,000 light-years from where you are sitting right now. Invisible to your eyes, but warping the paths of stars you could see if you knew where to look. M87 star, 6.5 billion solar masses. Event horizon larger than our entire solar system. Light takes 2.5 days to cross its shadow. First black hole ever photographed. Its image published in April 2019, confirming predictions Einstein made a century earlier. Ton 618, 40 to 66 billion solar masses. Event horizon 40 times the distance from the Sun to Pluto. Powering a quasar brighter than 140 trillion suns, visible across 10.8 billion light-years of cosmic distance. More massive than all the stars in the Milky Way combined. Phoenix. Estimated 100 billion solar masses. Event horizon 100 times the Sun to Pluto distance. Light needs 71 days to orbit its circumference. Possibly the most massive black hole in the observable universe, sitting at the theoretical limit of how large these objects can grow. These are not hypotheticals. These are not thought experiments. These are objects that exist in the same universe where you woke up this morning, ate breakfast, scrolled through your phone, lived your ordinary life. They are as real as the chair you are sitting in, as real as the planet beneath your feet, as real as the star that warms your skin. And they are waiting. Not actively, of course. Black holes do not hunt. They do not seek prey. They simply exist, warping space-time around themselves. And anything that wanders too close falls in. They are patient beyond any patience you can imagine, because patience requires the perception of time passing, and time at the event horizon has slowed to nearly nothing. From the perspective of the universe outside, these black holes are essentially eternal. They have outlasted the lives of stars. They will outlast galaxies. They will be among the last objects to exist in the cosmos, fading away through Hawking radiation over timescales so long that the current age of the universe is a rounding error. The universe built these objects. It used gravity and matter and time, the same ingredients that built you, and it created monsters of almost infinite density and scale. This same universe, following the same laws of physics that govern the atoms in your body, produced something so extreme that it breaks the rules we thought those laws implied. You are made of the same fundamental forces that made these things. You are gravity's sibling, in a sense. Carbon forged in stars, water molecules assembled in interstellar clouds, organized into a pattern complex enough to wonder about the scale of black holes in a YouTube video on an ordinary Wednesday. The universe is stranger than you ever imagined. And now that you know, you can never unknow it. Every time you look up at the night sky, you will remember that behind those gentle pinpricks of starlight lie galaxies, and at the hearts of those galaxies lie supermassive black holes, each one large enough to swallow everything you have ever known without noticing it was there. This is the true scale of a supermassive black hole. This is what the mathematics revealed over a century ago, what astronomers confirmed over decades of patient observation, what physicists continue to study because even now, even with all our knowledge, there is so much we do not understand. The universe made these things. and the universe made you capable of understanding that it made them. That alone should keep you awake at night, staring at the ceiling, marveling at the fact that anything exists at all. The true scale of a supermassive black hole is not a number. It is not a comparison. It is a doorway. And on the other side is everything you thought you knew about size and time and the nature of reality, revealed as a comfortable fiction you told yourself to get through the day. Step through. The universe is stranger than you ever imagined, and it has been waiting for you to notice.